Okay, so this is it. This is the end. This is the end.
I just think about the James Franco.
No crying today, okay? Just because this is over. All right, I don't want any tears.
Engineering stochastic.
Okay, we have to finish up 3.8, and there was one example I didn't do. So let's do this, and we're going to do 3.9. I handed out the notes for 3.9. That's it. It's just one page, one theorem, and that's it. So, okay, so we are trying to find the line integral over a vector field. So this was work, and we're given a curve C, which is the intersection of a plane and a cylinder, and we're given the vector field here. And we're going to use Stokes' theorem for this, but let's go ahead and first take a look at what C looks like. All right, so we have a plane and a cylinder. Let's draw the cylinder first. So in three-dimensional space, our cylinder is going to open up through the z-axis. It has a radius of 3. So our cylinder looks like this. And then we have a plane that slices through that, right? Because the plane is at an angle, so it's going to have to slice through somewhere, right? So our plane cuts through this. And where it intersects, wherever it intersects, we're going to get this curve C. And we will orient this where we're going to rotate about this curve. If we were looking from the top down, it would look like counterclockwise. So that's our orientation. Right it? Got it? All right, that also means that when we convert this to a surface integral, our surface S right here, the normal vectors will be pointing up, right? Well, they'll be tilted, but they'll have a z component that's positive, all right? Okay, so the theorem, that wonderful theorem from last class, says that if we have a line integral over a closed curve, we're doing f dot dr, that this becomes the double integral over s of the curl of f dot ds. So that's Stokes' theorem. And S is the surface that shares as its boundary the curve C. So we have this surface right here. This surface would qualify because its boundary is C. And what do you want to do first? I mean, you want to just go ahead and get the curl first, see what that looks like? Okay. All right, so let's compute the curl of F. The curl of F is going to be del crossed with F. So partial with respect to x, partial with respect to y, partial with respect to z, crossed with x squared z, xy squared, and z squared. So we're going to cross that. This will give us a vector, and that vector will be, let's see, the x component is what? Partial with respect to y of this is 0, minus partial with respect to z of this is 0 again. So 0, comma. Now we do this one, and I'm going to do the reverse order. Okay, so partial with respect to z of this is x squared, and then minus 0, so just x squared. And then finally this one, partial with respect to x of this is just y squared, partial with respect to y of that is 0, so y squared. Okay, so that is our curl. Make that a little smaller. All right, so I'm going to now write this down. I'm going to replace the curl with that vector, and then we'll see what we do from there. So double integral over S of the vector 0x squared y squared dotted with ds. And now it's kind of our choice how we do this. So any ideas on what you want to do here? This is This is our new vector field, right? This is kind of like the f from the formula, right? This is the thing I was trying to get you to see last class. Like this is no longer f for us, right? The curl of f is our new f for our surface integral. So that means this is our p, our q, and our r. And when would I want to use p, q, r? If I was going to be doing what? Yeah, if I was going to do a shortcut, if I was going to do like the surface is a function of two variables. In this case, our surface S, because it's a plane, right? This could be looked at as a function of x and y if I solve for z, or you could look at it as a function of x and z if I solve for y, or a function of y and z if I solve for x. It could be any of those, but I'm going to go with the one I think that makes most sense, and that's this surface is a function of x and y, right? So I'm going to use that special case. Z is a function of x and y. So S is z is a function of x and y, and that particular function is what? What is the particular function of that surface? 1 minus x minus y. Now I will need to get some restrictions on x and y, right? I will need to look at the shadow of this onto the xy plane and look at that, and that's going to really set itself up for what? Polar, some sort of polar conversion when I get there. But I am recording. I'm recording. I'm recording. Can't see that dot. Okay, it is. All right. So what formula am I going to use? This integral becomes the double integral over d. These were those special ones that I wrote on the board last class, right? Negative. So our normals are pointed upward, right? So I'm going to just use the formula as I gave it to you. I thought about printing it out. You know what I'll do is I will print out the page, or I will post in Canvas the page that has these formulas. Where the heck is it? Okay, I will post that page updated with the corrections because there was a typo in it. I'll post that in Canvas as its own single page in the where the formulas are in Canvas, and you can print that out and bring it to the test. That way you have all three special cases readily available. All right? So I'm using, just for your information, I'm using negative p partial g with respect to x, and then minus q partial g with respect to y, and then plus r. Notice I'm using a different notation here. Instead of writing partial of g with respect to x, I'm just writing g subscript x. That was a different notation we had for partial derivatives. So that's what I need. So what goes in here? Partial p, negative p, 0. So that's just 0 times partial g with respect to x won't matter, but what is it? Negative 1, right? That's partial of g with respect to x. And then minus, what's q? X squared, but then times partial of g with respect to y, which would be negative 1. And then we have plus r, and what's r? Y squared. I'm going to do all of that dA. And what does that clean up to be here? X squared plus y squared. dA. So I'm now doing this double integral, right, in terms of x and y. And I need to now find my restrictions on x and y. But because of the shadow of this onto the ground, right, this right here is d, it's a circle, so I'm going to go to polar. So I'm now going to let x be r cosine theta and y be r sine theta. And, well, x squared plus y squared will be r squared. So this integral is going to actually be really nice, isn't it? What are my restrictions on r and theta here? 0 to 2 pi and 0 to 3. Good. And you got the 3 from the fact that the cylinder has x squared plus y squared equals 9, which means the radius is 3. Right? All right, so this double integral becomes integral, let's go 0 to 2 pi first, 0 to 3, and then this is r squared. But because I went to polar, need another r, so r cubed dr d theta. And I'm not going to work this out. I'm just going to tell you what it is. It's 81 pi over 2. Okay, so you integrate with respect to r, plug in 3 and 0, subtract, then integrate that with respect to theta, and plug in 2 pi and 0. You should get 81 pi over 2. Sound good?
And then, like, the other way is whenever you dot f with the normal vector. With respect.
Okay, so the other way would be if we dotted f with the normal vector. Would we want to do that here? Could we do that here? As long as your normal vector doesn't change on this surface.
Okay.
And it is a plane, right? So what would that normal vector be? It's 1, 1, 1, right? However, the normal vector has to be unit length. So you'd have to divide it by its own length, which would be the square root of 1 squared plus 1 squared plus 1 squared, so root 3. So you could use this. Okay? Here's the problem with, here's the issue if you did that though. Let me just show you. Had you not done this, you need to know what the surface area of that is. Okay? So if you dot that together, if I did this instead, double integral over s of this dot n, right, ds, that's what that would become. Then when I dot this normal, let me just put the normal in here. 1 over root 3, 1 over root 3, 1 over root 3, ds. Then dot that. All it does is pulls a 1 over root 3 out here, right, out of the double integral. And then you still have x squared plus y squared, right, ds. This is different because it's not this one, right? You would now need to get this to be a double integral over d, or you'd have to use the formula for this. The formula for that is the square root of the arc length part, right? So it would wind up killing off the root 3 again, and then you'd be back to here. Yeah. The times that the normal is convenient is when the normal vector is like 1, 0, 0, or 0, 1, 0, like I, j, or k. Because then it's just like it kills off so much of the stuff. Yeah? It could be done. It's just, it was easier to do the other shortcut. I realize it starts to get pretty messy here with all this stuff because you've got all this options, right? All these options of what you can do, which formula, like when does it switch from, when does it switch from this to this? Like understanding when that happens, it takes some time to get used to that. I get it. Been there, done that. Okay, that's it for 13.8. And I gave you the homework last time, numbers 2, 6, 8, and 10. All right. We are now going to go back and we're going to look at divergence theorem, which is 13.9. But I want you to understand the divergence theorem is there to help us do flux. What we just did, Stokes' theorem helped us do what? Well, Stokes' theorem allowed us to turn this into curl F, right? ds, right? Like this. So Stokes' theorem allowed us to do work, right? We could do work along a closed curve in three-dimensional space using a surface integral, right? Divergence theorem is going to allow us to do flux. Now, do you remember what flux is? Flux is, that's flux, all right? It's not, look, this is flux also, but it's the flux of the curl. So somehow the line integral is the flux of the curl. Divergence theorem allows us to do flux with something, and it's very awesome with div. Okay. All right, so there's the theorem. I printed it for you. It says that if you have a surface, right, that is closed, and this is the important thing, you have to have a closed surface. That closed surface will enclose a solid, and that solid we call E. So let's just take a very simple example of a surface, a sphere, right? The outer shell would be S, but it encloses a solid, which is that ball inside, that would be E. Understand? If you have a scenario like this where a surface encloses a solid, and if you're trying to compute the flux over that surface, the flux over this surface, which was like the net flow out of the surface with respect to the vector field, all you have to do is take the triple integral of the div of f with respect to volume. So we're going to convert a flux integral into a standard old triple integral, a scalar triple integral. Because div of f, remember the div of f is not a vector. The div of f is a scalar. So when we take the div of f, we're going to get a scalar function. We're going to do a triple integral of a scalar function. Now, I'm not going to prove this theorem. I didn't prove Green's theorem. I didn't prove Stokes' theorem. Those proofs would probably take at least 45 minutes for me to get through each of those. And I could invest that time into class showing you the proof, but I don't think that it's really worth the time. Okay? The proofs are pretty awesome, though. I mean, you can Google it. I've seen a couple of proofs on Khan Academy of these that are geometric proofs that are pretty nice. So if you're interested in seeing the proofs, the one for this one's, the ones that I've seen are all they try and do is show left hand equals right hand side. Left hand side equals right hand side. And they just work it out. But, all right, so no proof. Sorry. We're just going to trust it. All right, let's do a problem. So I don't have any more notes for this. I have your homework assignment there, page 829, problems 3 through 13. Now all I'm going to do is some examples. So the first example I'm going to do is I'm going to go back to 13.7, because 13.7 was when we were doing flux, and I'm going to look at example 5. So 13.7, example 5. This will look familiar, I hope. Remember this problem? I think that we did that at the beginning of class last time, I want to say. Maybe not. You remember it, though? Okay, so what we had to do here is we had to, first of all, break this surface up into two surfaces. We had the green surface here, which had normal vectors pointing this way, and we were able to use that normal vector form of flux. And then we did the bowl part on the back side. We defined that surface, and it was a special case, and we were able to do that, right? But does this surface enclose a solid? No. Yeah? Does it enclose a solid? Yes? Okay, so since this surface encloses a solid, if we call the solid in here E, according to the divergence theorem, the surface integral over S, the vector field dotted ds, like this, should be equal to the triple integral over E of the div of F dv with respect to volume. And do you see it? What's the div of F? So div of F is the partial with respect to x of P plus the partial with respect to y of Q, and then plus the partial with respect to z of R. So you're going to look at the vector field and take the partial with respect to x, y, and z and add them up. So what do you get? Partial with respect to x of P is what? 0. Plus partial of Q with respect to y would be 1, and then plus partial of R with respect to z would be -1, and this adds up to be 0. And that means that this is the triple integral of E0 dv, which is just 0. And that's the answer we got.
So, assuming that you're going to, that's a good example, but the restrictions for volume.
We'll do a problem, trust me. We're going to do some problems where we don't get 0.
I was
Yeah.
Way longer, right?
Yes, it did.
You were lying.
It did.
No, he said
It took us a lot longer
45 seconds.
to do it with the div.
Yeah.
Yeah, I think I was within 45 seconds. I had to explain a lot of stuff, I guess. Like if you knew the formula for div, this should only take you about 10 seconds because you just calculate div and you go, shit, that's 0, and I'm done, right? You just want to give you a bunch of these? You want to give you a bunch of flux problems where the div is 0 on the final? All right, so yeah, moving on. I mean, there's really nothing else to talk about here. The answer we got, if you go back and look in your notes, I believe like one of these, like on one surface, we had to break it up in 2 surfaces. We got pi and negative pi, and then they wiped each other out and got 0. All right. Now, the next problem I'm going to do is not a problem I did in class. It's actually a problem that you are supposed to do for homework in 13.7. So this is probably the first time you're going to see this. If you did your homework, problem number 29, so I'm going to write this down. This is 13.7, problem number 29 from the homework. They gave you a vector field, and the vector field was x, 2y, 3z, and they gave you a cube. Your surface S was a cube with vertices plus or minus 1, plus or minus 1, plus or minus 1. And they wanted you to calculate the flux. Okay? That's what they wanted. They wanted the flux through this surface. So if you look at this cube, let's draw this cube first in 3-dimensional space. Let's go x, y, and z, z up here. I don't like this. Oh my gosh. Okay, x, y, z, it doesn't matter. All right, so I'm going to go and draw this cube now. We have every possible combination. So we have like 1, 1, 1, 1, 1, 1. Then we could have like negative 1, 1, 1. Then we could have like 1, negative 1, 1, right? All of these different possible. And you just get this cube. So out 1, over 1, up 1, out 1, over 1, down 1. And then do them all, and you get this cube. Do you get what the cube looks like? The center of the cube is the origin. Okay. So when we look at that cube, we're supposed to do this flux on it. We would actually, if we did it without the divergence theorem, we'd have to define 6 surfaces. Now, the good news is that the normal vectors for those surfaces would be nice vectors to work with, because we could use like I hat this way, right? Negative I hat out the back, J hat this way, negative J hat, and we could use K hat, negative K hat. So those problems may have, I don't know how long it took me to work it out on the homework video, but probably longer than it's about to take me. So let's do this with the div. I can do that. I can use the divergence theorem because this is a solid inside of this, right? We do have a solid enclosed by S. That solid is E. So what I want to do is a triple integral over E of the div of F dV, which is the triple integral over E. And now I need div F. So what's div F? So what's the partial of that thing, those things? What is it? So 1 plus 2 plus 3? So 6 dV. We all good with this? Div? Okay. And that's just a constant. So I can pull that out. 6 triple integral over E of 1 dV. What's that? The volume of the cube. This is the volume of the cube, isn't it? Volume of E. So let's figure out the volume of this. And just be a little careful here, because it's It's not 1, 1, 1. Like the sides aren't 1. They're actually 2, aren't they? So each side is 2, 2, and 2. So the volume of that is just 8. So you get 8 times 6 is 48. And that's what you would have gotten if you did your homework. 13.7, number 29. Look, when is the divergence theorem not going to help you, though? When it's not enclosing a solid. So in that case, you have to do it, right? You have to grind it out. And that's what I told you on the final. In order for me to test you on flux, I'm not going to give you a closed surface. I'm going to give you a surface that you must go and compute the flux on. All right, and then it'll be your choice. If it's a shortcut, you use a shortcut. If it's normal vector, you can use a normal vector. Or you can do the formula the way it appears first time I presented it, which is like f of r of uv dot r partial r cross partial u, all that stuff. All right, nice, nice. Okay, let's keep going. Let's go back to 13.7. Notes 13.7. And let's do example 6. That one look familiar? We did that. It took us a little bit to get that. We had to break this surface into 4 surfaces. We had the front side, the back side, the bottom, and then this curved part. And remember this right here, this is z equals square root of 1 minus y squared. This front side is x is 2, I believe. Yeah, 2. The back side is x is 0. And then the bottom of this would be z equals 0. So those are the different planes that we have along with the curve. Now this surface encloses a solid, doesn't it? The solid E, we could say. And what we will do is see what the div looks like. Let's just look at div real quick. What's div f here? 2x plus 2y plus 2z, which I could write as 2 times x plus y plus z. Okay, that's not as good as getting a constant, but it's, you know, it would have been nice if that was 0, but it's not. Back in your notes, anyone have this problem we did in class? What did we get as a final answer?
2 pi plus 8 over 3.
2 pi plus 8 thirds? I'm going to put that up here. 2 pi plus 8 thirds. That's what we should get as an answer, all right? Okay, so there's my div. So I'm going to set up a triple integral over the solid E of 2 and then x plus y plus z dv. So now I'm back to a scalar triple integral. And my variables are x, y, and z. All I need to do is see like how I can define that region E by placing restrictions on x, y, and z. Volume of, well, we're not getting, this is not the volume of the cylinder. If this was a 1, that would be the volume of the cylinder. But this is not a 1, so we can't do it that way. How do I construct the, what I'm trying to come up with right now are restrictions on x, y, and z for this triple integral.
Don't x and z already have restrictions?
What?
Don't x and z already have restrictions?
Okay, so you could do, what's one thing you could do here?
For x, you go to
X goes from what?
0 to 2.
0 to 2. And then y would go
From 0 to square root of 1 over.
negative 1 to 1. Negative 1 to 1. Now, what you're doing here is, what I think you're doing is you're looking at this solid and you're looking at its ground, like the ground, the shadow of this on the ground. And you're seeing that if you draw that shadow, here's x, here's y, it looks like that. Wait, hold on. No. It looks like this. This goes, I drew it out of scale here. This is 2. The x comes out 2, right? Goes back to 0. And then the left and right, how do you know that's negative 1 and 1? What's that?
You plug z as
Z is 0. Yeah, you could do z is 0 and then just square both sides. And you get 1 equals y squared. Y is plus or minus 1. Yeah? So negative 1, 1 and negative 1 here. That would be your bottom, right? That would be the base of this solid. And then what would be the top? What would be the part up here? The bottom would be 0, and then the top would be root 1 minus y squared. So I could do this. I could go integral from 0 to 2, integral from negative 1 to 1, integral from 0 to root 1 minus y squared, blah, blah, blah. And then I could say dz, dy, dx. Yes? It does matter what order. These two don't matter what order, but this one has to be the integral. That's right, because it depends on the other one. So do you agree I could do that?
Yes.
I'm not going to do that, though. I'm going to do something else. I'm going to, because I did it this way. I've done it this way, and I've done another way, and I like the other way better. I just want you to know you can do it this way. Instead of looking at our region like this, what if we look at this going back into the YZ plane? Okay, so here's Z, here's Y, right? Then what would the shadow look like on the YZ plane? On the YZ plane, it would look like a half circle. So I'd have like, here's Y, here's Z, and then it would go like this, wouldn't it? That thing. And it would go 1 and negative 1 here.
That's your base, right?
That's your base, but the base is actually up against that wall instead of down.
And your height will be 2.
Your height would come out this way and go back to 0, right? So I could leave 0 to 2 on x and y. I mean, sorry, on x. I could leave that. But this, I'm going to do something different. Because that region right here is a polar region. Like, it's good for polar, isn't it? So what I could do is I could say I'm going to let y be equal to r cosine theta and z be equal to r sine theta. And then my radius, I need to come up with restrictions on theta and r. So help me out with these. 0 to what? Pi. Just pi, because I'm only going to draw half the circle. And then my radius will go from 0 to 1. Right? Do y'all see the difference between these two approaches? You get the same answer, okay? So what I'm going to do now is I'm going to switch this over. It's going to be a function of x, r, and theta. R is between 0 and 1. Theta is between 0 and pi. Go with me? Yes, no, maybe so? I need to rewrite the integral now. So when I rewrite this integral, it will become 2. Don't forget the 2 out front. And now I'm going to have limits of integration here. And I should probably start out with well, I can do any of these, can't I? Because they're all constants. So I'll just do x first. 0 to 2. That means dx is the last one, right? And then let's do the theta next. 0 to pi. And I have what? It'll be d theta here, and then 0 to 1, right? And that'll be my dr. Yes, because we went to polar, right? So that r has to come. What about x plus y plus z? Well, x is just x, okay? X is just x. We never did anything to x, did we?
No.
What's y, though?
It's
R cosine theta. And then I'm going to run out of room. Plus y, which is r sine theta. And then all of that, we have the r, then dr, d theta, dx.
Is this symmetrical coordinates?
This is cylindrical. But remember, cylindrical is really polar in 3D, right? You're doing the same substitution. It's just one variable is going to not change. Also, keep in mind, why did I do y is r cosine theta, z is r cosine theta? Why did I not do x is r cosine theta and y is r sine theta? because it's on the YZ plane, right? I mean, you have to realize that. When you go to polar, it's not always x is r cosine theta, y is r sine theta. All right, we good? Yes, I'm going to go ahead and compute this now. So I'm going to pass the r through. So 2 triple integral 0 to 2, 0 to pi, 0 to 1. And then I've got xr plus r squared cosine theta plus r squared sine theta dr d theta dx. Integrate with, I'm going to take this the whole way. I want to get to 2 pi plus 8/3. So integrate, the first integration is with respect to r, right? So 1/2 xr squared, right? That's the antiderivative of this. Here, plus 1/3 r cubed. Cosine theta is like a constant, so it just comes for the ride. Same thing here. 1/3 r cubed sine theta. And I'm going to evaluate all this at r equals 0 and r equals 1. And then when I'm done there, d theta dx. We good? Continue. What happens when you plug in? Let's plug in 1. So when we plug in 1, we just get 1/2 x. Plug in 1 here, we get 1/3 cosine theta, right? And here we get 1/3 sine theta. When we plug in 0, everything goes away. So all we have is 1/2 x plus 1/3 cosine theta plus 1/3 sine theta d theta dx. Which is equal to 2. Okay, now I'm going to integrate again. This time I'm integrating with respect to theta. So what is the antiderivative of 1/2 x with respect to theta? 1/2 x theta. Okay, and then what's the antiderivative of positive 1/3 cosine theta? Positive 1/3 sine theta. Okay, and then what's the antiderivative of positive 1/3 sine theta? Negative 1/3 cosine theta. All right. I'm evaluating this at theta equals 0 and theta equals pi. And then after I'm done with that, integrate with respect to x. All right, what do we get here? So plug in pi, you're going to get 1/2 pi x. So 1/2 pi x. Okay, sine of pi, 0. Cosine of pi, negative 1. But then times negative 1/3 is plus 1/3. Right? That's what I get when I plug in pi. I'm supposed to take that and subtract from that what I get when I plug in 0 for theta, which is going to be 0. Sine of 0 is 0. Cosine of 0 is 1. So negative 1/3 dx. And you can do minus minus is plus, and that'll be 2/3 right there, right? So now I'm going to have 2 integral 0 to 2 of 1/2 pi x plus 2/3 dx. Let's go ahead and integrate. What happens when you integrate this with respect to x? You're going to pi x squared, and you're going to have out front 1/4, because remember the 2 comes out, right? So, or you'll have another 1/2 joins that one. So I have 2, that's this 2. Then I have 1/4 pi x squared. And then the antiderivative of 2/3 with respect to x is 2/3 x. Understand? That's the antiderivative. Evaluating that from 0 to 2. or 2 to 0, however you want to say that. 2 goes in, 2 here, you get 4, right? 1/4 of 4 goes away, you just get pi. Plug in 2 here, you get 4/3, right? Plug in 0, they both go away. We're there. We have 2. We said that this was going to become pi, and this is going to become 4/3. And distribute your 2 through, and you get 2 pi plus 8/3. Now, I don't remember how much work it took for us to do it when we did it the other class. It was a lot. This kind of took a little while also, but I think the actual work in here is easier. Like, yeah, but the thing is, it's like we can't mess up any normal vectors, or we can't, like there's a lot of things that could go wrong when you have 4 different surfaces. Like if one of those goes wrong, you're in trouble. Here, the integral, we had it right away. As long as we do the integration correctly, everything should work out. Okay, cool, good. All right, the next one is a homework problem from 13.9. So it is from this section. I'm going to do one of the homework problems. So this is from 13.9. I'm going to do an even problem, number 6. And here's what they give you. They give you a vector field. The vector field is the vector field x squared y z, and then x y squared z, and then x y z squared. So that's your vector field. And they give you a surface that is the combination of these 6 planes. You have x is 0, y is 0, z is 0. X is some constant a. They're not telling you what it is. That's greater than 0. Y is some constant b, which is greater than 0. And z is some constant c, which is greater than 0. So let me try and draw what that is. And what they want is the flux over that surface. So x equals 0 is the yz plane. This is the xz plane. This is the xy plane. This x equals a is a plane that's been moved out, and it's parallel to the yz plane. This one is parallel to the xz plane, and this one is parallel to the xy plane. So it looks like this. X, y, z. So I have the ground, right, that's z equals 0. This wall right here, which is this, y equals 0. This back wall, which is x is 0, right? And then I have 3 more planes. X equals a brings this plane out. I'm not going to make them the same length. They don't have to be the same length, so. All right, something like that. Do you see that? It's like a rectangular box. What is this front side, this plane right here on the front? What's the equation of that? X is a. What about this side one? Y is b. How about this top one? Z is c. Do you see them? And then the bottom is z is 0. The left side is y is 0. What am I missing? Backside. Backside is x is 0. There's your surface. Calculate the flux. Well, I really hope this is a div problem because I like that solid, right? A triple integral over that solid would be very easy to do. I do not want to have to do 6 surface integrals, right? So let's compute div. The div of f here is not going to be 0, sorry. It is going to be what? 2xyz. That's a partial of the first part with respect to x plus. Same thing again, right? 2xyz and then plus 2xyz. Any questions on that? That's just 6xyz. Okay. I'm willing to go after that. All right, so I'm going to say the inside of this is E, right? So the surface integral over S, which is the combination of all this surfaces, ds, the flux, should be equal to the triple integral over E of, what, 6 xyz? dv, right? Triple integral with respect to volume is what we're doing here. 6 can come out. I can take care of that. That's no problem. What about your variables, x, y, z? Are we gonna have control over those in this for this region? Absolutely. I mean, that's x is between 0 and a, right? Y is between 0 and b, and z is between 0 and c. I mean, that's as clean as it can possibly be. Well, I guess I could give you actual numbers other than a, b, and c, but that's pretty straightforward, right? I think we're in business. So we get equals 6, I'm bringing it out. X, Y, Z. Let's go 0A, 0B, 0C, X, Y, Z, DZ, DY, DX. Did I get the order right there? Yep, I've got the Z is the inside, Z has C, Y is B, X is A. Am I allowed to do this? As long as these variables are completely separated from each other with multiplication and not mixed together, I can do that. Right? I have multiplication. And those are all constants, so I'm allowed to do this. My first integral will be from 0 to a of what? X dx. The next one, 0 to b, y dy. And then last one, 0 to c, z dz. I mean, you could just go and integrate this with respect to z first and plug in, then y, then x. We'll get the same answer. I just think this might be a little shorter. Because I think once I integrate one of these and see what the answer is, I think I can just, you know, we say this in mathematics, WLOG, without loss of generality, which means that if I do this, the answer I get here, I can basically draw the same conclusion from this for this one and this one because even though I'm kind of generalizing it, I'm not losing anything when I generalize that. Okay, so the antiderivative of this would be what? Let me just do that on the side here. That would be 1/2 x squared evaluated 0a, right? Plug in a, you get 1/2 a squared. Plug in 0, you get 0. So this one should turn into 1/2 a squared. This one should turn into 1/2 b squared, and the last one should turn into 1/2 c squared. And then just put your halves out front. So you get 3/4 when you reduce that fraction, 6/8. 3/4 a squared, b squared, c squared. Or you could put a, b, c in parentheses and square that. That's it. That's your flux. So as you move the planes, right, as you adjust where these planes are and how far out they are, that will have an impact on your flux. Here's exactly how it will impact the flux. It'll impact it by 3/4 of the square of the value of the A, the B, and C respectively. So I think that one was definitely worth doing with the div, don't you? Okay. All right, this is number 7 out of the homework. Number 7. 13.9, number 7. I believe I'm down to my last 2 examples. This one, and then we have one last kind of interesting problem. All right, so we have a vector field F, which is the vector field 3xy squared, x e to the z, and then z cubed. So finally, a vector field that's somewhat interesting. And then we have as our surface that we want to compute the flux on is the, I'm going to draw it for us. It's a cylinder, and the equation of this cylinder is y squared plus z squared is 1. All right? The front surface here, this one right there, is part of a plane that cuts it off, and that's just x equals 2. And then the back side of this, let me do it this way. This back side right here is also a plane, and it's x equals -1, not 0. All right, so it's not on the YZ plane. It's a little further back. You all see that? That's our surface. So if we were going to do this with a surface integral, we would break it up into, if we were going to do this with a surface integral, how would you do it? Yeah, so you could do this front surface and back surface, no problem, right? But the cylinder is not a function of two variables. That cylinder, so you have two options. You could break it into two pieces, a top piece and a bottom, which means you'd have two more surfaces. Or you could do this surface here, you could do an R of UV, and you could draw it. Let's do it, let's practice. How would you draw that? Dun, 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 dun. Dun, 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 dun. How would you draw this cylinder? U cosine V. Do you need the U? Cosine V? What's the radius of that cylinder? 1? So which components of my surface function would need to be the cosine and sine? Y and Z. So I would do something like cosine U, sine U. And then what about the V? I just gave it away. What about the x component? It would be v, right? And then our u would be between 0 and 2 pi, right? That would draw us circles. And then our v would be between what? -1 and 2. Okay? That's the other option, is that you define this surface, and for this one you use the R of uv, and there is no shortcut, and you've got to use the grinded out formula for flux. Do you remember the grinded out formula for flux? Yeah, it's like this. It was F dot ds, right? Like that. So then you have to go F and evaluate it on this vector curve, and then you replace S with magnitude cross. Okay, so look, it just turns into the cross of the partials dotted with that F, but we're not going to do that because we have divergence theorem. Right? Because this surface encloses a solid, we should be able to do this with a div. So let's calculate div F. It is 3y squared plus 0 plus 3z squared. So it's just 3y squared plus 3z squared. I need to do the triple integral over E of, I'm going to pull the 3 out, y squared plus z squared dv. Hold on, I've got too many things going on. Yes. I think, yes. What?
Oh, I said we just go to polar.
Go to polar, yes. What? Which is polar, yes. They're all this. Yes. Yes, yes, yes. Look, if in three-dimensional space, it is really called cylindrical coordinates. But one of the dimensions isn't going to change. The other two are what go into the conversions. So that's the two-dimensional integral. Right? If we take one of these out, it's called polar. The third integral is the variable that we don't mess with, and we don't touch it. So, you know what I'm saying or not? I mean, you say polar and cylindrical, you're talking about the same thing. But if you're in two-dimensional space and you say we're going to go to cylindrical, that doesn't make sense, because cylindrical is for 3D. Okay, so this is very similar to the problem we just did a second ago, right? Right? What's the conversion that I'm going to make? Y is r cosine theta, z r sine theta, and what am I going to do with x? Nothing. I'm just going to let it be x, right? I mean, I'm not changing it at all. So what are my restrictions? Let's get all the restrictions. R, theta, and x. We need restrictions on all of them so we can set up our limits of integration. So r is between 0 to 1, theta, 0 to 2 pi. We're going all the way around, all right? And then x, negative 1 to 2, like that. This is 3 triple integral of, well, I'll do the limits of integration in a second. What's y squared plus z squared? R squared. But then we also have the r, so r cubed. D, this order doesn't matter, right? So I'll go r first, then I'll go theta, then I'll go x. And just make sure I get my limits of integration right here. Theta 0 to 2 pi, and r 0 to 1. I lied, there's two more examples. I said 2, I meant 3. So this is the first of 3 examples that I have to go. I'm not going to compute this. 9 pi over 2. I think that beats rewriting that as r of uv and doing all that cross product partial stuff that we would have had to have done. I hope you're sold on this theorem. Okay, that's very nice. It's also called Gauss's theorem. I think I have that on there. Do y'all know who Gauss is? You've heard of him, right? Yep. Gaussian elimination. When you do matrices and you do elimination, it's called Gaussian elimination. Gauss is one of the big guys, the big hitters in mathematics. Brilliant, brilliant mathematician. Have y'all heard this story about Gauss when he was a kid? With showing his teacher the sum of the integers. I usually show my classes this, but I'll show it if I have time at the end. He was a genius. Huh?
showed it to us in linear.
Yeah, oh, he did? Okay, the sum of the integers? Okay. Okay, so I'm going to do number 13 now. So I'm basically doing all your homework. The reason why is because when I did this last time, I'm not doing all the homework problems. This is most of them, though. Is that I didn't want to go make the homework solution video, so I just did most of the homework in class. So I'm kind of doing the same thing now. All right, so check this one out. This is going to be different. Here, you're given a vector field, and the vector field is defined to be the magnitude of r times r, where r is equal to the vector x, y, z. Okay. What the heck is that? Well, let me give you the surface. The surface is the top half of the unit sphere. So it's the upper hemisphere, and then also the surface x squared plus y squared is less than or equal to 1 with z equals 0. All right, we'll get to the surface in a second. Let's talk about that vector field, because that vector field is something different than what we've seen before, right? It just looks different. Yeah? All it's saying is that you've got three-dimensional space here, and if you go out to a point, so go out x, y, z, pick me a point here, x, y, z, And if you want to know what the vector field is at that point, the vector that's emanating out of this, the vector field at that point x, y, z, then what you're